All right, and I believe we're live. Great. So for this review session, I'm just going to be going over homework problems from homework 4, 5, and 8, and just showing you guys kind of some of the concepts that are going to be on the test and kind of the ways to go about it. I'm not doing homework 6 or 7 because I did that in my last video. And what you guys should be expecting for material content wise is, flow nets, hydraulic permeability kind of stuff, settlement calculations, and consolidation parameters. The whole time rate consolidation will not be on this test, so there's no need to study that over the course of tonight. And with that, here we go. And like I said, if you guys aren't talking, just mute your mic, and if you guys just stop me whenever throughout this whole thing. So 6.31, soil borings made at a site near Chicago indicate that the top 6 meters is a loose sand and miscellaneous fill. With the groundwater table at 3 meters below the ground surface, below this is a fairly soft blue-gray silty clay with an average water content of 30%. The boring was terminated at 16 meters below the ground surface when a fairly stiff clay was encountered. We need to make reasonable assumptions as to the soil properties and calculate a total, neutral, and effective stresses at 3, 7, 12, and 16 meters below the ground surface. So since we need to make so a lot of this kind of stuff, you can go online or go in a textbook and find typical values for a lot of these soil parameters. So for what we're going to be doing here, I'm going to say, get my pen going. The dry unit weight for sand, so sand, for this upper sand fill is going to equal 13 to 15 kilonewtons per cubic meters. And so this is our range, and we're going to just pick right in the middle because, there's nothing too bad about that average. So dry equals 14 kilonewtons per cubic meter, and we're going to say that gamma saturated equals 15.0 kilonewtons per cubic meter. So those are our assumptions, and we need, so we're going to use phase relations to estimate the saturated unit weight for the clay. And we're going to assume for the clay that rho S equals 2.7 megagrams per cubic meter. So let me scroll down a little bit. When we're doing this, we're going to say, all right, the saturated density is 1, and this is just going back to our phase diagram stuff like you guys did on the last exam, over 1 plus rho S over rho W, and just plugging and chugging. In this problem statement, it said we had a water content of 30%. So our Y saturated for the clay will be 19 kilonewtons per cubic meter. So we do that, and then we find the stresses at every depth. So let's say the stress at depth 3, for example. So that will just be the unit weight times Z. So we got 19 times 3 Oh, no, sorry. We need the dry. So for this one, so is my mic having issues?
No, you're fine.
Okay. So based on, we say we're at depth 3, which means that the groundwater table is 3 meters below the ground surface. So we're like right at that line, but we're not going to be considering water in this calc because we're not technically underneath it. So that's why we're going to say the 14 here, which will give us the 42. And and you guys seem to be pretty knowledgeable in being able to calculate stresses, pore water pressure, and effective stresses. And so, it's just reiterating the same thing at different depths and including the stresses above it. So, our equation is total stress is the effective stress plus the pore water pressure. So that's how we get these different parameters right here. So say let's do 7, right? So we know, let's just look at, so we say, all right, we got unit weight at Z1 plus the unit weight at Z2. So we know 14 times 3 plus the unit weight, which I believe at this point we are now in that we're now at the clay layer. So let's use the 19 times 7. Oops, I used the wrong number here. Oh, sorry, it's still sand. Right? So whatever this unit weight is, I'm not going to waste your guys' time because you guys understand how to do this stuff. It's just reiterating it all the time for the pore pressure, the stress, and just rearranging this equation. So does anyone have any questions, concerns, comments? If not, we're going to keep rolling on. All right. So 7.15, given the soil, cylinder, and test setup from this example, the actual dimensions as follows: AB equals 5, BC equals 10, CD equals 10 centimeters, and DE equals 5 centimeters. Calculate the pressure elevation total heads at points A through E. And in centimeters water, and plot these values, whatever. So just kind of looking at everything, we know E is at 0. And then the distance from D to E is 5. So at point D, we're at 5. So let's just say, and this is all elevation head. So we're at 0, we go up 5, and then from D to C, which is 10 meters, so now we're at 15, and then, we go up another 10, so we're at 25, and then 30. So simple enough. But now we want to calculate the hydraulic gradient. So to do this, let's calculate the hydraulic gradient from, so we're going to calculate I from B to D. And so I is going to be the change in head over the length. So we're just going to say, well, 30 minus 0 over 20 is going to equal 1.5 centimeters. And then, because we want to find total head. So to do that, give me 1 second. We're going to find the head at C, D, and then the length from D to C. So we said, all right, oops. So HC equals the head at D plus the chain or the hydraulic gradient times the length of D to C. So the pressure head at C is 0, and then plus 1.5 times 10 centimeters. So we get 15.0. So we get that, and that's our total head at C. And then from HD to C, we get HC minus H. So 15 minus 15 equals 0. So that's, so when I go down here, when we do all this stuff for what we're given here, this is what our graph will be. And, you know, here it's saying that we have a linear relationship for the head elevation. And then for the pressure head, you know, we go up like this, that way there. And then for the total head, we're kind of zigzagging everywhere. If I could draw a straight line. So, and what I remember grading from everyone's homework assignments, everyone seemed to do really well on this problem. So I'm not going to go into it too in depth. But does anyone have any questions? So, all right. So we had a question of why is the pressure head at C0? So I'm trying to see how I can best explain this. So yeah, so the comment is, I don't understand why the pressure head at C is 0. Does it have to do with it being in the middle of the soil? Yeah, I would say so. So because it's here, you know, and when we calculate everything, at A, we'll get a total head of 30. At B, we also get a total head of 30. And at C, we get a total head. This is total head, not pressure head, because the pressure head at A will be 0, 5, 0 at C, and then -5 at D. And then 0 again at E. So when we look at this graph, that's what we get for pressure head. So, Okie dokie. All right. So if I were you guys, I would get real familiar with some flow nets for this exam, because I think this will be a big topic. So we got this problem. We got a sheet pile wall that has been installed partially through a silty sand layer, similar to the one shown in figure 7.13. Assume a sheet pile 12 meters long penetrates 6 meters or halfway into the silty sand layer, thickness of 12 meters for this condition. So we need to draw the flow net using 3 or 4 at most flow channels. And then if the water height of the upstream side is 5 meters on the downstream side, compute the amount of water flowing under the sheet pile per meter of wall if the coefficient of permeability is this, and then compute the maximum hydraulic gradient at the downstream side of the sheet pile. So to do this problem, we're change my colors again. We're going to do equation 7.20. So we know Q equals K. Oops, that's not what I wanted to write. HL and just double check this. I think it's NF. And if I'm wrong, someone just correct me, but NF over ND. So let's just bear with me as I try to redraw this. Or actually, I'll just use this diagram down here. So we want to draw a flow net, and it tells us how many channels we're supposed to have. So to do that, I'm gonna start here. If I can draw it right. So that's going to be 1. We're going to do another one up here. And then we'll do one more right here. Because the way that the soil wants to flow is that it wants to go underneath the wall for the shortest path. And then if it can't do that, it's going to want to go the next possible route. And then if it can't do that, it's going to want to do that. And also remember, these are all supposed to be at perpendicular angles and look nice, but I am not an artiste, so I apologize. And from the flow net, we'll find that this NF equals 4, and then ND is 4 times 2, which equals 8. And the reason I say that is because we want to find the amount of blocks here that are pretty much isolated, right? So we got 1, 2, 3, 4. And the reason why we multiply it by 2 over here is for each side of the wall. So we have that, and then our head loss is going to be 5 minus 1, which equals 4 meters. So we have, and we're given that our K is 3.1 e to the negative 4 centimeters per second. And remember, this e to the negative 4 is just me saying, 3.1 times 10 to the negative 4th. This is just how I write it in my calculator. So now we have everything to put it in our equation here. So I'm just going to, so we've done part A. We've made the flow net. Now we're doing part B. You know, if the water height on the upstream is 5 meters, on the downstream side 1, which is our head loss, you know, the difference between the two. Compute the amount of water flowing underneath the sheet pile, you know, per given the permeability. So now we have everything, and based off of our flow net. So we're going to say, all right, Q equals 3.1 e to the negative fourth centimeters per second, but we want this in meters per second. So, you know, doing just a quick unit conversion, we should get to the negative 6 meters per second. And then times 4 meters times 4/8, or 1/2. So therefore, we'll get Q equals 6.2 e to the negative fifth cubic meters per second per meter of wall. So that's part B. And now part C, compute the maximum hydraulic gradient at the downstream side of the panel. So to do that, we'll need our hydraulic gradient again. So I is going to, like we said in the last problem, over L. So, but we know that the change in head loss is in correspondence with the flow nets that we've already predetermined. So delta HL is just the head loss over NB. So we got 4 meters over 8, which gives us 1/2 meter. So if we were to draw this perfectly, we can, you know, and scale it, we can, you know, measure it pretty finely, and you would get a number, distance L from, you know, scale the, you know, the distance L from the flow net, where L is the flow length in the first exit square immediately, you know, of the sheet pile. So if we were to scale this and, you know, do it real finely, we get L equals 2.375 meters. So let's just go with 2.4. That's pretty close. So to calculate this new hydraulic gradient based off of this length, we got 1/2 divided by 2.4. And we'll get somewhere around 0.21. And that will be our answer. We got any quick questions or any concerns?
Can you scroll up just a little bit?
Yeah. Or how far?
I guess keep going.
To the top?
And then, yeah. Okay. Okay, thank you.
No problem. And I'll try my best to reference as many equations as I can. But I'm not always the best at that. So anything else before I keep moving?
Hey, Ian, where'd you get that 6 meters per second in the Q calculation there at the bottom?
Talking about this?
Yeah, where'd you get that from?
Okay, so I didn't get it anywhere. This is my notation. So instead of, you know, writing out 10 to the negative 6 every time,
Dude, you got it.
I write e to the negative 6 because that's the quick way to write it in your calculator.
No, yeah, I thought, never mind. You're good, man. Sorry.
No problem. So, and I'm kind of bad about always being consistent with my notation. So if you guys see anything else like that, just let me know and I'll clarify. Also, my handwriting's bad if you have not noticed. So moving on, 7.26, using the data of figure 7.18, compute the total head, piezometric head, pressure head, and elevation head for point C, and assume any convenient datum. So to do this, I'll leave this up for about 5 to 10 seconds on where do you guys think the most convenient datum would be for this? Because there's two ways to do it, and they're both right.
Water level.
Now at the water level.
Yeah.
Actually, I'll do that in blue because it's water.
The way that I would do it at the bedrock, just because that's how I like to do it. But
Yep. So perfect. So there's two ways to go about this problem. For what I'm going to do, I'm going to do at the bedrock, which is a little bit different than what you guys have done in class. So this might be a little bit helpful in case you guys get stuck in a bind, like on the test or whatever. But both are appropriate to do. So I'm going to, and like Dr. Benoit said, this is more typical to assume it here. But in my mind, when I do this, it's like, well, this doesn't move. So going on, so I'm assuming that my datum is at the impervious boundary. So at point C, so I'm going to calculate my total head at point C, which so we got total head minus, our flow net, I think D, times the change in head. So where this is the total head for the whole reservoir, and this being, okay, let me get my colors out. So this is for the total head for the whole reservoir. And this is the number of equipotential drops for the whole reservoir to point C, which is where we're going to try and find it first. So to calculate the total head at point C, it's going to be 42 because that's the distance, the whole distance from here to here. So that'd be total head. So 42 minus 5 times, because if we go through this, we'd be like, well, 1, 2, 3, 4, or 1, 2, sorry. 3, 4, 5, 1, 2, 3, 4, 5. You're just counting squares at that point. So 5, 12, and 10.4. So, and this is for C right here. That looked ugly. So when we do this, it'll be, HC will be 36.2 meters. So one thing to note, though, is that where we're getting this point at is that since they're directly above each other, and we're not having to deal with funky stuff, this is also going to be the total head down here. So, and then our elevation head, since this is technically, so at our elevation head for C will be 28 from the bottom, because it's not, we're not have that 30, we got this 2 meter embedment into the soil. And then our, let me use E. I apologize. And EC prime, since our datum's there, is 0. So to calculate the pressure head, so let's do the pressure head at C. We're going to take this 36.2 and subtract the distance between C to C prime, which will give us 8.2 meters. And then we'll do the same thing for HPC prime. It's 36.2 minus 0. So this is the pressure head here and then here. So you guys can significantly see the difference between the two. And then that's all we need.
How did you get 5 drops again from, are you going from, okay, I'll just let you answer.
Yeah. So 5 drops. So it would, so I think it's based on, so this is 1, because it's full squares, not, that makes a border with, this boundary. It can make a border with the sheet pile wall, but not with impervious boundary. So it'll be 1, 2, 3, 4. And this is, this is kind of halved. So that's 5. So that would be our number of drops.
Couldn't you also just use the numbers that are circled, like the 1, 2, 3, 3.5 to 4? Don't those
you
also
can
represent?
you can do that too.
Yeah, just throwing that one out there.
You know what? That's perfectly fine. So just make it easy, make it as easy as possible on you guys. There's nothing wrong with that. Any other questions? Oh, and at the end, I will allow people to ask just general questions about anything and everything. So, but if no one has any more questions pertaining to this problem, we're going to keep moving on.
Hey, what about the delta HL? Real quick, the 12 divided by 10.4. Where'd you get that from?
So the 12 divided by the 10.4 is, so you got this height here, right? And then the 10.4, because the sheet pile wall is 10 meters. And then the 0.4, I believe.
Take the bottom there.
Yeah.
Okay.
And this also.
Oh, okay.
Because C and C prime are pretty much in close relation to each other. So it's it's the difference between like because you got this dip here. But piece of metric head. I think so. This is another one of those things where geotechs like to name the same thing 10 different ways. So the piezometric head is just our elevation head. And, and as you guys very well know, it gets only worse in consolidation terms. So just, piece of metric head, elevation head, because we want to know how, basically, is it boot high water or is it knee deep water? That's the important, that's the T. So any other good questions? Nope. All right. 7.30. So for the completed flow net of this figure, oops, that's not what I want. Try and make this a little bit bigger. So for this flow net, compute the flow under the dam per meter of dam if the coefficient of permeability is this. So this one's going to be just short. So remember this little nifty equation we used earlier? Well, we're going to do it again. So we're going to use equation 7.2 where Q equals the coefficient of permeability times the head loss over NF and D. So as we're going through this, we know NF is 3. 1, 2, 3. 3 channels. And we're gonna, count the number of drops. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Essentially, you can maybe count this as like a half, but we're just gonna go with 9 for our purposes. And the head loss, which since this is completely drained on the other side, is just gonna be 6.3 meters. So now we got everything for our equation. And let me just scroll down a little bit. So Q equals K, HL, NF, and D. And I'm just going to plug and chug. We got 4.2 e to the negative 6, which I'm sure it has it in centimeters per second, but we just want to be consistent with metric units, so we say meters per second because the coefficient of permeability is just a parameter of velocity. So times 6.3, and then we got the number of channels over the number of drops, which we will get so we will get 8.82 e to the negative 5th, which I'm going to write it real nice down here in blue because we're dealing with dirt and water. This is what makes us better than mechanical engineers. Because if there was no water, then a mechanical engineer could do what we do. Which is in terms of flow per meter of wall. So, and that's it. That's the end of this problem. Any questions about that? Nope. Okay. So, scrolling. As you guys can tell, I do not have great handwriting, so I have to give myself some extra space. So now we're getting into the consolidation stuff. So we got these pressure and void ratio data determined from consolidation tests on an unsaturated clay specimen as follows. we need to plot the pressure void ratio curve on both arithmetic and semi-log scale, determine the equations for the virgin compression curve and for the rebound curve for unloading, and starting at 1280 kPa, what are the corresponding modified compression and recompression indices for the soil, and estimate the stress to which this clay has been pre-consolidated, according to how Casa Grande did it. So as you guys can see, I've already went ahead and plotted it like this. This is not typically how we leave things for consolidation tests, because it doesn't really tell us anything, because all we know is that it kind of moved and decreased linearly, if you had to be really rough with it, and then just kind of rebounded a lot. So this is very tiny. Make this much bigger. And my Excel did not want to be nice to me today. So this is our, our consolidation curve, in semi-log. And can anyone tell me, so do we have a recompression, a full recompression index in this graph? Because we can calculate the recompression, but do we have it to make it easier, like the necessary part of it that makes it easier on us? I'll leave this up for about 5 seconds. So the answer is no. Like we can still calculate it, but we don't, if everything was a perfect world, it would look something like this. So that's not what I wanted. So the reason why, because which is, it kind of sucks for you guys because you guys can't get your hands on a real consolidation test. But the way that these kind of things go is that we take the soil, because the whole thing about clay is that clay has a memory, so it remembers everything it's ever done, every stress that's ever encountered, and then so what we're trying to do in this test is push it beyond its limits and see how it reacts. And also the bad thing about clay is that when you disturb it in any manner, so we take our SPT test and we pull it out, so we try to preserve it as best as we can, but when you dig down and then you stir it up, then it loses all memory. So this is for a different class, but there's a lot of discrepancies about using SPTs today. But so this is the curve that a nice perfect curve here. And if we were going to do it easily, we would just say, okay, oops, if I could draw this straight, we would just draw a line through the loop and then grab our points from there. But we don't have this in this scenario. So what we're going to do is that we're going to approximate it from a bunch of lines. And I cannot draw well in this or on paper, so please bear with me. So the first thing I want to do is that I want to find my compression index, because we have more than enough data for a compression index. So to do that, so what we're wanting is C sub C. And what we're going to do is that we're going to take, basically just find the slope of the line. And when I'm doing this, I want to make it as easy as possible as I can. So I want to use like nice rounded numbers, and sometimes you're going to have to draw a couple of different lines. So what we want is that we want a line tangent to somewhere about here. And I'm just going to extend this line out. So, and sometimes we don't draw it perfectly. So let me draw it one more time. Something like that, yeah. So, we draw this line out, and sometimes you got to do it multiple times till you get it right, or till you get something that makes sense. So from drawing this line here, I'm going to say, well, I want to pick a point here around 10,000, just because it's a nice round number. And yes, you are extrapolating, but this is, to me, this is a little bit easier. And then we want to get a number around, here, where it's 60. And if I had put all my little log scales, it would make it much easier to grab all this. So I got those, and then you just get your E values from there. And we would get C sub C equals 1 minus 0.3 over the log of 10,000 over 60. And when we get that, C sub C equals 0.32. And so that's our compression index. Now, how are we going to get our recompression index? So, as kind of as I stated earlier, if we had the nice loop, we would just get it from here. But you have to remember, in our test, we're loading this clay up, and then it's going, and then we're releasing the pressure, and we're recording it. So what we're going to do is that we're going to go, if I can draw this decently. Now draw a line like this. And from this line, we're going to pick another value from 10,000, just because it's an easy place, to get things. And then we're going to, pick a value from right here. So just from both ends of the lines. Let me scroll. So to find our recompression index, C sub R, we got, E1 minus E2 over the log 10,000 over 1. So when we do that math, we'll get 0.065 for our recompression index curve. So, and we also need to determine the modified compression and recompression index. So from this problem, we know that our initial void ratio, so write this in green. So we know E naught is just 0.864. That's what we started with. So, and I'm going to use equation 8.9. So the C sub C sub epsilon is just our C sub C over 1 plus E naught. So we got 0.32 over 1 plus 0.864. So we get somewhere about 0.17, and if there's some rounding errors, it could also be 0.16, within the ballpark. And we're just going to do the same thing for the modified recompression curve. So C sub R epsilon, which will be 0.065 divided by 1 plus 0.864, which will get 0.035. And let's also try to get the pre-consolidation pressure. And there's, I may not be able to do this as much justice as your book does. Let me try to figure it out and figure out which part of your book explains this really well. Okay, so if you guys were to go to so if you guys went to figure 8.6 in your textbook, that is a really good tool to help you determine what the pre-consolidation pressure would be for your problem. So we'll find that our pre-consolidation pressure, it will whoop. So our pre-consolidation pressure is probably going to be somewhere like in here. And, you know, if we were to draw down to find that stress, we would find that our pre-consolidation pressure is 220 kPa. So that's all that we needed for this problem. And like you guys saw in your homework, this is kind of compounding into 8.9. So, you know, we need to estimate the thickness and all this kind of stuff. So to do this problem, we need to find our OCR. And this is, you know, when you guys are doing settlement or consolidation, this is usually one of the first steps that you need, because this will tell you which equation that you'll be using. So sigma p prime over sigma v naught will be 220 over 126, which is given to us, which will be 1.75. And we're also gonna, you know, as I'm writing this, I always want to write this too, because if this is true, then this will help us out as well. We're checking to see if it's greater than the pre-consolidation pressure. Because if it is, then we'll have an over-consolidated equation where the settlement will be C sub C plus C sub R, those two long equations. So I'm gonna do that over here. And we got 126 plus, it was told to us that the change was 285, which we get 411, which it is greater than 220. So we luck out a little bit. It's just, you know, you might get a little bit of carpal tunnel, but that's okay. It's worth it. Yeah. So now that we have this, I'm going to go to equation 8.19b, where SC equals C sub B. I think C sub C epsilon. And if I'm writing this wrong, please let me know. Log of sigma p prime over sigma v naught plus C sub C, or oops, C sub R epsilon H naught log, I'm going to write this over here, sigma v naught prime plus delta sigma v over sigma prime p. So we from the last problem and everything we've been given, I'm just going to plug and chug. So we got 0.034 times 7 log of 220 over 126 plus 0.17 times 7. Oh, sorry. I use 0.5 times the log of 126 plus 285 over 220. So when we do this math, we should get somewhere around 542 millimeters. And that'll be our total settlement. And to find our strain, we're going to say strain equals delta E1 over 1 plus E naught. So delta E1 equals because we know strain is just settlement over our soil layer. So for layer 1, we'll just get 0.0137 times 1 plus 0.864. and that will give us 0.0255. And then for delta E2, we'll just do the same thing, and it's, you know, layer 1 and 2, or, you know, just the different stuff. And we got 0.0208 times 1 plus 0.864 gives us 0.0388. So, and since we're now changing scenarios in this B part, we're saying that the pre-consolidation pressure is the equals the initial pressure. So we'll get 126 kPa. So that, you know, and again, that changes our equation. So instead of using 8.19, we're going to use 8.13. So now it's C sub C, which equals C sub C, H naught log sigma prime V naught plus. And this, and even though we've changed our parameters, this is not going to change. So this is still 285. So plugging and chugging, you know, we'll get that the settlement will be 611 millimeters. And to get the change, the normally consolidated change of void ratio, so our delta E and C, is just going to be, you know, S over H times 1 plus E naught. So we got 0.0873 times 0.1 plus 0.864, which will get 0.0949, where the strain will be 0.087. I already stated that, my bad. So yeah, and that's all we need for this problem. Any quick questions? I got one more problem, and I know I'm starting to run over time, so I'm gonna try and go through this last one at a not slow rate. Nope, okay. 8.32. So we have you know, as part of a construction project, a 7.5. God bless. Trying to make it bigger for you guys. So, as you know, we got a 7.5 thick layer of clay to be loaded with a temporary 3-meter thick sand. The figure shows, you know, where the water table, you know, all of our parameters. We need to calculate the effective vertical stress in the middle of the clay layer. So at 3.75 meters below the water table before the sand layer is applied and after consolidation is complete. And based on your answer in part A and the compression curve characteristics, calculate the settlement that will occur under these conditions. How much will the clay heave when 3 meters in sand, you know, blah, blah, blah. So this is kind of just a little bit combo of a little bit of everything what we've talked about today and, you know, for the past few months. So to do, you know, sigma V naught, we're just going to take the middle, which is what we want to assess, times, you know, 20 minus 9.81 because we're taking the water out because we want effective stress. So we get 40.1 kilonewtons. I don't like writing kilonewtons over meter squared. Let's just be practical and say kPa. So that's part A. Now for part B, we got delta sigma V, which equals 3 times 16, which equals 48. And then the pre-consolidation pressure equals 74. And this is all information I think we've gotten from a consolidation test. Yeah, right here. And so we need to check the OCR. So the OCR is just sigma p prime over sigma v naught, so 74 over 40.1, which the OCR equals 1.85. So we're probably going to have an over-consolidated soil. So we do. So we're going to use the big long settlement equation. So C sub C epsilon H naught log of sigma P prime over sigma V naught. And I know in your guys' textbooks, there's a bunch of different ways to write these equations. Just make sure that you match your variables to what you have. So, and then we'll have C sub R epsilon H naught log of V naught plus delta sigma V over pre-consolidation pressure. So we have our big nasty long equation, and I'm just going to plug and chug from what we have. So 0.03, 7.5 log of 74 over 40.1 plus, I'm going to write down here, log of 40.1 plus 48 divided by 74. And when we do all that math, we'll get 162 millimeters settlement. So for those who don't go by shoes in centimeters or use a metric on a daily basis, sometimes it's nice to put these things into perspective. So I'm going to convert this to inches. So this, and sometimes when you need to put things into how you think about it to be like, oh, is that a lot? Is that a little bit? So in real units, this is 6.4 inches, a settlement. This is all, it's a pretty, it's going to shift your doors. You're probably not going to be able to close doors very often anymore with this much settlement. So just keep that in mind when you guys are taking your test tomorrow. Just like, well, does this make sense? Is this practical? Is this realistic for the soil? Clay can compress up that much. So just try to do the reality checks. And so now we're going to do our swell, which is going to be C sub R H naught. And this is also known as C sub S, in case anyone tries to throw that at you. So V for V naught. Sorry about that. So we'll get our S swell to be 0.03 times 7.5 log of 40.1 plus 48 over 40.1. So the swell settlement is 77 millimeters. And let's just put that into perspective again. So that's about 3 inches. So, and that's all I got for you guys today. Those are the answers. I just figured, I know everyone's been really stressed out and kind of burnt out on the homework, and I've seen people kind of struggling. So I figured I'd go through and just do homework problems today so that everyone kind of had the solutions to them. So I'm done talking. I'm going to give you guys the floor. Do you guys have any questions for me or want me to clarify anything? The floor is yours. And I'm going to stop my recording here as well.